Hello everyone, welcome to week 10th live session for NPTEL Semiconductor Device Modeling and Simulation course. I am Om Maheshwari and today we will be solving some questions that may help you with your assignments as well as your exams. In this week we will be talking about hydrodynamic modeling as an extension of DD model, carrier balance, energy balance, momentum balance equations, and how to solve these equations. So let us start. So if you remember, this is the drift diffusion equation that we had seen earlier. This is the drift part, this is the diffusion part. Okay, so if you see in this equation, so drift diffusion is defined in thermal equilibrium, and thermal equilibrium means the temperature of lattice is equals to temperature of electrons equals to temperature of holes. But under very high electric field, electrons gain energy or the carriers gain energy, and their uh, temperature is increased and is not equal to the lattice temperature or room temperature. So this brings a temperature gradient, a localized temperature gradient, which is also now a cause of current. So the drift diffusion equation is modified as follows, where we have the drift component, diffusion component, as well as a temperature gradient component. And how to find this electron temperature is, it is based on some certain modeling. I won't go into the details of the model, which you can see from the videos. So this is how the electron temperature is modeled. It depends on the electrons energy relaxation time, mobility, and the electric field, and this quantity is also known as the critical electric field. Okay, so a few more important uh, things in this before we start are the energy conservation and momentum conservation. So these are the you can say the energy balance or the momentum balance equation. So this is the rate of change of energy of electrons under the influence of some field E with saturation velocity Vs, and this is the energy loss due to scattering, and in steady state both of these terms will be equal, that is the rate of change of energy of electrons will be 0. In similarly in momentum relaxation, this is d nothing but dp by dt. Here this is the force term, and this is the again mvs by tau. This is the change in momentum due to scattering. And another important thing is velocity overshoot. So what is velocity overshoot? If we have a sudden change in the electric field, let's say at time t equals to 0, we have a sudden change in the electric field. So the drift velocity Vd is given by q tau by m into E. This is nothing but mobility, right? Mu into E. Mu is q tau by m. And tau is inversely proportional to the electric field. So when there is a sudden change in electric field, E1 to E2, the tau would decrease. But the change in this time would not be so sudden. It will take some gradual time to come to this level. It will not be as discrete as the electric field. It is not like that. It will take some time and then come down. So the velocity first initially increases because V is tau into E. So if E is increasing, tau should actually decrease, but tau is taking some time to go down. So V actually increases a little bit, then it comes down. So this is known as velocity overshoot. So this is a very important phenomenon which is not uh, captured by the drift diffusion model and is captured by the hydrodynamic model. So that is the importance of hydrodynamic model. The hydrodynamic model basically captures two things. First, it is the velocity overshoot. Second is the carrier temperature. So these two things are captured by the hydrodynamic model. Now, just give me a moment. I think my audio is not working. Let me reconnect. Okay, so I think now I can. Okay, so now I think I can hear properly. Am I audible?
And now it is audible, sir.
I'm not able to hear you.
And now it is audible, sir. Sir,
Okay, let me reconnect. Just a moment. Okay, I don't know. I'm not able to hear anything. So if you have any questions, please do type in chat. I don't know what the issue is.
Uh, Hello, sir. It is audible, sir. Hello.
So I discuss the modified density again, but I, I hope you are able to hear me.
Sir, your sound is also very less, sir.
So let me go back to the modified density equation. So here earlier with the diffusion model, uh, is it still very good?
Hello, sir. Am I audible? Hello, sir. Hello, sir. Am I audible? Hello, sir.
Okay, so sorry for the technical difficulty. So let me start again. Okay, so I started with the overview of drift diffusion equation and the motivation, like why do we need the hydrodynamic model. So earlier we had seen this is the drift diffusion equation, right, for the current density, and this is the where we have the electric field is the drift part, and where we have the change in concentration gradient is the diffusion part. But this drift diffusion equation was defined in the thermal equilibrium condition. The thermal equilibrium condition is the lattice temperature or the room temperature is equal to the temperature of the electrons equals to the temperature of the holes. This is the thermal equilibrium condition. But what happens when we have a very strong electric field is electrons gain some high energy due to which their temperatures, the or any carrier, even if electron or hole can gain high energy. So due to which their temperature Tn or Tp may increase. So so this gives us another uh, gradient of temperature inside the device, and this local gradient is responsible for some additional current, and which is defined by and dt is just some temperature coefficient, like we have a diffusion coefficient, and it's dependent on the gradient of the temperature, like concentration gradient. It's very similar to diffusion, just instead of concentration gradient we have a temperature gradient. And so this is a very this is a model to calculate the temperature of the uh, electrons in a, and I won't go how that it is derived. So Professor Dikshit has derived it in the videos. You can go through it. But basically, it depends on the energy relaxation time, the mobility, and the electric field on the square of the electric field. And this term mu times tau is also called as critical electric field. So Tn, that is the electron's temperature, is equals to TL, that is the lattice temperature, times 1 plus E is the current electric field times divided by EC, that is the critical electric field whole square. This is how you can find the electron temperature Tn. Uh, is there any doubt in this? Okay, we'll come to that. Yeah, it's a good question. We'll come to that in future. So tau E is a energy relaxation time, which we find maybe you can see from here. We can find tau E. So so these are like momentum balance and energy balance equations, you can say. So what this just mean is the change in energy of an electron is equals to what force you are applying to it. This is basically is uh, this is velocity. Vs is velocity. E is the some, you can say, electric field. E is the electron charge. So what force it is facing minus the energy it is losing the uh, due to the collisions with uh, not collision, actually due to the scattering with the phonons. Okay, so under uh, uh, steady state, this energy gained by the electron and energy lost by the electron would be same. So this would be zero. So from here we can determine tau E, and I think here this is the formulation E OP equals to E Vs tau E, and tau E will be EOP by E Q E Vs. Okay. Right. So tau E here is the energy relaxation time. We'll also see how these where do these equations come from. in a while. But for now, I think the significances of tau e is just it's kind of a scattering time, how defining how the energies change, uh, how energy changes with collisions with optical phonon. Okay, so now here just to motivate more, what is the significance of hydrodynamic model? So we already saw we need to calculate something like this, that is some temperature variance, which was not there in the drift diffusion approach. So one of the things is we need a model for carrier temperature, which is captured by the hydrodynamic model. Another thing is velocity overshoot. So what is velocity overshoot is, uh, we have seen tau is inversely proportional to energy, right? So this tau is inversely proportional to the energy. So and energy is okay, energy is electric field. So Vd we know is mu times E, and mu is defined as, this is mu, q tau by m. Now if there is at time t equals to 0, if there is a sudden change in electric field from E1 to E2, right? So since tau is inversely proportional, it will decrease, but it will not have a sudden decrease like the step change in electric field. It will slowly decrease. So since Vd is proportional to both tau and E and electric field, so since tau is slowly decreasing and E is suddenly increasing, this Vd will suddenly increase, and then slowly it will come down depending on how lower the tau is. So this peak with the time is actually not captured by the uh, drift diffusion model, and we need to capture this we need hydrodynamic model. So velocity overshoot and the carrier temperature dependence are the two things that the hydrodynamic model captures, which is missing in the drift diffusion model. Okay, so let's go ahead now with the questions. So the first question is, okay, so just read the first question. I'll be back in a minute. Just give me a moment. I'll be back. Please see the first question. Okay, so do we have an answer for this? Okay, so actually the answer is it is computationally very expensive. So it requires solving multiple partial differential equations, which makes it extremely expensive to solve. And it has to be solved across all the nodes, across all the grids in the structure, and as well as in space dimension, in time dimension, and multiple quantities are there to be calculated. So that is why it is uh, computationally expensive to solve. Okay. Next question. What does carrier heating have? What effect does carrier heating have on the velocity profile? So what would happen if the carriers are more heated or energized? Well, what will happen to the velocity? So will velocity increase or decrease? What will happen? Okay, why will it broaden? What will increase? Sorry. Okay, so okay. So let's say this is the velocity distribution. Let's say this is number of carriers and this is the velocity. So initially, let's say you have some profile like this. Uh, let's say this velocity is V0. Now you change your temperature to, or carriers are heated to some higher temperature greater than, let's say T greater than T0. So just by intuition, also you can say when temperature increases, your velocity will increase, right? Kinetic energy will be more. This temperature increase will give more kinetic energy to the carriers. So that means your velocity must increase. So if this is the velocity direction, your distribution has to shift in this direction. More and more number of carriers will have a higher velocity. So this will go something like this, right? So basically the velocity distribution will shift to some higher velocity. Let's call it V1. It will not broaden or not get narrowed down because let's say you're still in this first case, you still have some temperature T0. So yeah, option C is correct. So even at T0, some electrons have, some carriers have lower velocity, some have higher velocity, some, and most of them have some peak, some velocity V0. So if we increase the temperature, same thing will happen. Some will gain some, still have some lower velocity, some will have some higher velocity, and most of them would have some velocity V1. So this distribution will not change, just it will shift. Okay. Next question. Identify the correct statements if the length of the device is more than the elastic scattering length and the Fermi wavelength, we classify it as diffusive transport. If the phase coherence length is more than the elastic scattering length, then classical laws are applicable. If the device length is more than phase coherence length, it indicates ballistic transport, or D, all of the above. So before going to this, let's first see what these lengths are. So phase coherence length is the distance an electron travels before suffering a phase change of 2 pi. Elastic scattering length is the mean free path between elastic scattering events, that is ion impurity scattering or something like that, where electrons collide with something which is stationary. Inelastic scattering is the distance an electron travels before losing energy, kT, that is typically phonon scattering. That is, electrons interact with some other moving, you can say, moving uh, entities such as phonon. So we have phase coherence length, elastic scattering length, and elastic scattering length. So diffusive transport is when L is the gate length. Your length of the channel is much greater than your elastic scattering and your lambda f. Lambda is just a parameter uh, which we call as Fermi wavelength. And it depends on the number of electrons and the volume of the channel. So for diffusive transport, L is greater than Le and lambda f. So what was our first option? If length of the device is more than elastic scattering length, that is L is greater than Le and Fermi wavelength lambda f, we classify it as diffusive transport. Right. So this one is correct. Let's see if others are correct. Second talks about when are the classical laws applicable. So let's see. So classical laws are applicable in two cases. Case one is L phase coherence length is less than elastic scattering length. Second one is L is much greater than lambda f. So let's see what the question is. If phase coherent length L phi is much more than elastic scattering length Le, then classical laws are applicable. Right. We see here this is it should be less than elastic scattering length. So this is false. Third one must also be false because all of the above is the still incorrect. So the device length is more than phase coherence length. It indicates ballistic transport. So what it's saying is L is greater than L phi, then it is ballistic. And in ballistic transport, L is less than Le and L phi. Right. This is also false. So only first one is correct. So ballistic transport is another transport regime. So let me just briefly tell you what is ballistic transport. Ballistic transport means like your channel length is so short that an electron travels through the channel without suffering any collision or scattering. That means the mean free path or the scattering length of electron is much more. That means Le or whatever you call it, lambda, MFP, mean free path is greater than the channel length itself. So within this channel length, there are no scattering events faced by the electron. So the mobility is very high. This is known as ballistic transport. Yes. Yeah. So ballistic. Uh, okay, this is not a consequence of this. Right? I'm saying what is the condition for ballistic transport. So let's say if you have an electron, I'd say it will strike with some atom or somewhere uh, to get uh, uh, like the scattering event will happen only after uh, let's say, okay, let me explain it this way. Let's say there is an electron which just scattered from this uh, charged ion. Now it will again travel with some velocity and it will again scatter with another charged ion only after its mean free path distance, which I can call as LE or lambda. Okay. Now, if your channel length itself is shorter than your LG is shorter than this mean free path, that is the distance between the two collisions is larger than your LG. That means within this LG, it will have no collisions. No collisions means no scattering, and no scattering, that is very high velocity. So this is ballistic transport, where there is no scattering or very minimal scattering. Does this make sense? So basically, mean free path or this LE is the distance covered by the electron before which it collides with some scatter or scatters again. That is the quantity defined by this LE or lambda. And if this quantity is more than the gate length, that means within this gate length there will be no scattering events. No, this is not a ratio. I'm just saying this is not a ratio. It's just it is not LE by lambda. It is LE or lambda. Both means the same thing. LE is, if you see LE's definition, it is the mean free path between elastic scattering events. It is LE or lambda, no ratio. Both mean the same thing. Okay. Okay. So next question. How is the energy balance equation derived in hydrodynamic model? So do you have any idea? Have you seen the video? Okay. So let me just briefly cover that. So how the hydrodynamic model is derived is we need a few things. Uh, we need the Boltzmann transport equation, that is this del F by del T is minus 1 by h cross del K E del RF Fe by h del K of F del F by del T by collisions. So this is the Boltzmann transport equation, which I think you would have studied in, like, I think last week. So to derive the energy balance or different balance equations required for the hydrodynamic model, we multiply Boltzmann transport equation with an appropriate function phi k. We'll know more what is phi k later, and integrate it with over the momentum k. So we multiply this whole equation by phi and integrate it with k. So that's what it is done here. Every term is multiplied by phi and integrated over dk in every term you see. So by doing that, we define some certain other quantity. So in each term, let's say this phi f dk is defined as the some average some average quantity. This is like some averaging function, so it is in some average quantity. This phi u is the velocity, so this is some kind of flux. This g phi is some kind of generation rate, and r phi is some kind of recombination rate due to collisions. So now if you see your equation becomes something like this, which looks very similar to continuity equation, right? So in continuity equation, you have del n by del t equals to del j plus g minus r, something like this. Yeah. So this looks very similar to continuity equation, but still it is not same because we don't know what this phi is. So now what we do is, let's say if we assume phi k equals to 1, then all these terms simplify to give you some certain terms which basically give you a term which is very similar, which is actually called the carrier density balance equation, which is very close to your continuity equation. It's very similar to continuity equation. We get this when we assume phi k is 1. It is missing some generation term, but it is very close to continuity equation. Now for momentum balance, we assume phi k as a function of some linear function of momentum, which we have assumed here is minus qhk by m star. So if we assume this is some final form of the equation where we get some the momentum balance equation reduces to this, which is the rate of change of current density. Is Wn is the energy, and okay, and in the energy balance equation we assume phi k to be function of k square, or we know this h core square k square by 2 m star is energy, right? From Schrodinger solution we get this. So we assume phi k in form of an energy which is actually dependent on k square. Then we derive the energy balance equation, which is this. Where this W's are the uh, energies, Fw is the energy flux, Jn is the current, E is the electric field, and tau E is your energy relaxation time. So the question was, how is energy balance equation derived in hydrodynamic model? Right, by phi k. So what we did was we did Bt into phi k and integrated, right? So but for energy balance we use phi k as a function of k square, right? Which is actually h cross square k square by 2m. This is specific for energy balance. For carrier balance, carrier density, we chose phi k equals to 1. For momentum balance, we chose phi k proportional to some k, I don't remember, I think 2 pi k something. What was it? It was qhk by m. Minus qhk by m. Yes. And for energy balance, it is this. So it is option B, right? Okay. So is this clear? All right. Okay. Next question. Under steady state for bulk uh, semiconductor with uniform electric field, energy relaxation time tau E is given by. So we again need, sorry, Yeah. So this is again, as I said earlier, also this found using this energy balance equation that we just calculated above. Yeah, we can see directly it is related to. Okay. This is the energy balance equation, and under steady state, this del Wn by del T becomes equals to 0. This also derivative term becomes 0. So we have Ejn equals to Wn minus W0 by tau. So this is the relation, and we equate it to 0, or tau E will be Wn minus W0 by Ej. So it is option A, Wn. Yep. So Wn is the energy, uh, some perturbed energy of the electron. W0 is the energy that was there in equilibrium. E is the electric field, J is the current density. Okay. Okay, so next, before going to the next question, let me just first discuss a very simple thing. So next we will talk about some numerical methods that are used to solve these partial differential equations. We saw like energy balance, carrier balance, and charge balance. We saw all these equations have this kind of form, right? So to solve this, we need some numerical methods in whatever simulation framework we use these equations. So we still use this grid kind of method, where I think we saw this earlier also, this forward difference, backward difference, these kind of methods. So this del u by del t, if it is a function of minus v del u by del x, so it is a relation time with position. So this how it is solved is let's say for forward central space, this kind of approach. How we solve it is uj n plus 1 minus uj n by del t equals to minus v times u n j plus 1 minus u j minus 1 n by del 2 del x. Now what is n and j? So if let's say this is the time axis, this is the space axis. So in time axis, the difference between the two nodes is delta t between n plus 1 and nth node. So when we have to do this delta t, we take the difference between uj n plus 1 minus uj n. And this j variable is representative of position. So in this axis, we take uj minus 1 and j plus 1, and the difference between, and this one is j, and the difference between all these, this will be delta x, this will be delta x. So by this central difference method, it will be j minus 1, sorry, j plus 1 minus j minus 1 by 2 delta x. This is what is done here. So basically the whole point of this is we need some numerical methods which help us discretize these partial derivatives. Right? That is the main crux of this, whatever I'm talking about. So there are various methods discussed in the uh, in the lectures, and they talk about the stability of those lectures, sorry, the stability of those methods. So there are some questions in the assignments based on that. So let me just discuss that. So first question is, which of the following condition must be satisfied for phase error to be zero in Lex method while solving hydrodynamic model equations? So Lex method is another method like this forward time centered method. There is Lex method. So this is the equation for the Lex method. Mu j n plus 1 equals to 1 by 2. Whatever this equation is, not important for me. And the stability criteria for this is if phase error is 0, if this term, actually this term is equals to 1, and which is v delta t by del x equals to 1. So which option will it satisfy? Option A. B delta t by del x equals to 1. This is the condition to be for stability of Lax method. Okay, so again, like just to tell you in terms of assignments or your exams, it is not important that you remember all these equations, but like these conditions under which they are valid, these are important to that you should try to remember. Like when it is stable and something like that. So there are several methods, like I think 4 methods discussed in the videos. I would recommend you remember all these stability conditions, like when this method is valid. Okay. Next method is, there is another model such as Dufort-Frankel method of discretization. It is unconditionally stable regardless of the step sizes. So there's the Dufort-Frankel scheme. So it is unconditionally stable without no matter what the step size is. So it is always stable. It is an explicit method. What Okay, we'll talk about explicit in the next slide. So basically here we know it is always stable, unconditionally stable. Sorry, I I I don't know why it is true, but it's just a condition that is just for information. It is not discussed in the videos like why it is always stable, but maybe it's just one of the numerical techniques that has some mathematics behind it. I don't know that mathematics, but it is always stable. Okay. So again, we have these stability questions. So before that, let me just talk. I think these two are still we have not discussed. This one we have discussed is unconditionally stable. So what is Euler's method? So again, it is another kind of method which has this finite differences in this form, and it is completely stable for, but it has some conditions. Stable only when this condition is satisfied. That is your delta t by k delta x square is less than 1 by 2, less than equal to 1 by 2. This is the condition when your Euler's method is stable. So Euler's method is explicitly stable for this condition. So this one is connected to this. No, we have to match the following. Dufort-Frankel, we saw it is explicit and unconditionally stable. This one is the C. Krang-Nicholson is this method. This is implicit and always stable. So what is the difference in explicit and implicit is, if you see in explicit, phi n plus 1, if we have to find, it is all only dependent on phi n terms. So we can calculate it a bit easily compared to those implicit equations, where implicit equation your phi n plus 1 is dependent on phi n and other phi n plus 1 terms also. That means we cannot solve it directly. We need some numerical iterations to where we will assume some initial uh, assumption like phi n plus 1 is equals to this, and we iterate slowly to get to the final phi n plus 1. So we need iterations to solve this, but this one is also always stable but implicit. So Krang Nicholson is implicit but always stable. Yeah, explicit means and implicit. plus 1 depends on phi n comma phi n plus 1. Yes. Okay. So this needs numerical iterations to solve. This can be solved directly. Okay. So answer to this will be 1C, 2A, and 3B, which is option C. Okay. Next is this. Ensemble relaxation rate in carrier balance equation is related to inter-value transfer by. Okay. Right. So basically, what this means is simply what is this delta n by delta t collision dependent on? It is basically change in density of change in the carrier density of electrons between the two states divided by your tau n is your carrier density relaxation time. This is also found from your carrier balance equation by changing that uh, del n by del t to 0, what we call a steady state condition. Okay. This B. Yeah. Okay. Fine. Next question. Calculate the conductivity given a relaxation time at room temperature of this. So we have tau n is 0.123 21 minus 14 seconds. Density of free electrons n equals to 8.5 into 10 to the power 28 per meter cube. Mass of electron is 9.1 into 10 to the power minus 31 kg. And electron charge 1.6 into 10 to the power minus 19 coulomb. So can you attempt this? How can we solve this question? Uh, yes. Yes, it is option A. So just for the recording, let me just tell how this is solved. So we know sigma is NQ mu, and mu is Q tau by M. So if you substitute, it will be NQ square tau by M. This is sigma. That is your conductivity. So by substituting all the values, N is 8.5 into 10 to the power 28. Q is 1.6 into 10 to the power minus 19 whole square. Tau is 0.123 10 to the power minus 14. M is 9.1 to 10 to the power minus 31. Okay, so if you solve this, you will get 2.94 10 to the power 6 science per meter. So please note it is per meter. We have given same values in per centimeter also, but since we have taken all the values, this was in per meter cube, this is in kg, this is in coulomb, and this is in seconds. So your answer will also be in meter units. Okay, so I have one more question for today. A MOSFET has a length of 90 nanometers. Width of the channel is 1 micrometer and the oxide capacitance is 20 femtofarad per micrometer square. Transconductance of this device is 1 millisiemens. The voltage applied across the drain and source is 0.1 volts. We have to calculate the field effect mobility. So before calculating, let's see what is field effect mobility. So there are certain types of mobility that are defined in these week's lectures. First is the effective mobility. Effective mobility is calculated with help of GD. GD is del ID by del VDS, and we take it in linear region. That means ID linear is mu n C ox W by L VGS minus VT to VDS minus VDS square by 2. Now if I do del ID by del VDS, it will be, let me call this term as GD, is mu n C ox. Right. So your mu, and here let me call it as effective. Mu effective here is GD into L by W C ox VGS minus VT. So this is your effective mobility. Effective mobility we calculated with the help of GD, that was del ID by del VDS. There's one more mobility, that is field effect mobility, which we calculate with the help of del ID by del VGS. This is called field effect mobility. So again, if I write my current equation, ID is mu C ox W by L VGS minus VT VDS VDS square by 2. Right? So if I do Cox W by L into VDS, right? Alright, so here now mu or mu field effect test will be equal to Gm into L by W Cox VDS. There is a mu field effect. So this is what we have to calculate in this question. So we have to find mu Fe equals to Gm transconductance into gauge length by W Cox VDS. Gm is millisiemen, L is 90. I'll write everything in centimeter. 19 to 10 to the minus 7. W is 1 micrometer, that is 10 to the minus 4 centimeter. Cox is 20 femto, 20 to 10 to the minus 15 per micrometer square. That is 10 to the power minus 4 into 10 to the minus 4. VDS is 0.1. With this, I'll get everything in centimeter square per volt second. That should, these units, I'll get my answer. Okay, so yes, you solve this, you will get, yeah. So this option A. Okay, so these are all the questions I had for today. If there are no doubts, we can close the session and we will meet next week. Yeah, yeah, yes. Yeah, I think that is enough for this. So, so whatever I discussed is the only thing that is given in the videos. So I took every reference from the videos itself. So with by watching the videos, I was able to solve all these questions. So I think you should be able to do the same thing. Okay, so there are some limited questions that I have solved based on some previous assignments, but I still recommend watching videos for because watching them once is not no harm, and you should watch the videos. At least you may learn something new which is not asked in the uh, questions. I only talk about those parts of the videos which help you solve the questions, right? Or give some bit of overview of some concept. But there may be few more things which are not maybe not there in these questions but are there in the video. So watching videos is definitely, I suggest you watch it. It won't take much of your time. You may need to give. So okay. So how do I solve these questions? I also watch the videos first and I try to solve it, and it takes me 2 hours. So I think you, yeah, I watched it at 2x and I am able to solve these assignments in 2 hours. So I think you can do also do the same. 2 hours is not a very big time you cannot give in your week. Yeah. So each video is almost 30 minutes to 40 minutes long. So I think there are 4 videos. So it will take you what 1 hour. If you watch it on 2x, it will take you 1 hour or some minutes to completely watch all the videos. Then if you just look at the assignment questions and you'll be able to see like much more uh, about the questions than before you had watched the videos. So how I do it is I read the questions first, like what the question is trying to ask. Then I watch the videos and then I can relate. Okay, this is the part where I saw like this is the part I need to focus on where there was a question in the assignment. Yeah, yeah. So just to get an idea like what kind of questions are being asked, right? Because if we don't know what is being asked, we won't be able to find it in the videos. We'll just watch it and we won't know where do we need to focus on. Do I need to focus on the derivation or which topic is important? That I don't know. I will know that only after I see the questions. So first read the assignment, then watch the videos, and then you can do the assignment. Yeah, this is week 10. I think. Yeah, week 10. I'll take 2 more classes as well as one summary session I'll take where I will try to bring some common questions from all the assignments or some summarize what is being taught, what has been taught, or talk about what is important. So I'll take 3 more sessions. Yeah. So it is scheduled for 2 hours only, but let's see if we have more to discuss, we can extend it. Oh, I'm good. Thank you. Okay. Okay. See you next week.